Hi everyone, this is Madhav and I wanted to create a quick video on integrals. I have to be honest, integrals are kind of my worst nightmare after having spent an entire university course memorizing formulas to calculate integrals. It's not very fun. I will say that sometimes I felt it very tedious to do the formulaic approach, so instead I'm going to talk about an approach to integration that just always works. This isn't like some kind of exam hack, this is an understanding kind of concept. So this is just to understand like what does it mean to get an integral. As you may have heard, integrals are about the area under a curve. So in our case, let's say I decide to show the area between, you see this weird line, it has a huge messy equation that would be hard to use formulas for, though you could. Let's say I want to get the area between this blue line, this orange line, and then the x-axis. Visually, I want to get this area. The approach to integration that, oh by the way, I think Desmos already knows the answer. I think it knows the answer using this approach. I can't be sure because I haven't looked at the code, but this is what the area will work out to be, and we're just going to figure out like how do we calculate that. So the approach that I'm going to talk about, it is an approach that computers will use when they don't have time to figure out like how do I clean up this mess so that I can figure out what the area under the curve is. They're just going to approximate the area under the curve. How are they going to approximate the area? Well, what might be convenient might be to take this curve that we have, this weird shape, and break it into more simple geometric shapes. One of the most simple geometric shapes that we have to calculate the area of is a rectangle, because you just take the base times the height. So that's what I'm going to do here. I created two rectangles. You can see that the two rectangles, they both only touch the curve, this blue curve, at these left points. And if I take the area of these two rectangles, clearly I don't get the area of the curve exactly, but it's a little bit of an estimate, a little bit of an approximation as to how I might get the area of this entire curve. Now, how might I make my estimate a little bit more exact? Well, you might say, okay, just take the area of this like triangle here and this triangle here. But again, we don't like triangles because like they have messy 1/2 BH areas. We just want to quickly calculate the area with base times height. So if we can't go and take, other geometric shapes, if we're only allowed to use rectangles, one thing we can do is let's make these rectangles more skinny. Here's what I mean. Instead of two rectangles, what if we had 4 rectangles, each with, half of the width of these original ones? You can see there's less area under the curve that we're not capturing in our formula. There's less area under the curve that we're not capturing in our 4 rectangles here. So we could simply go, okay, each of these is like half a unit wide, and this one's 1 unit tall, and then 1.64 units tall, 1 unit tall, what? 2.25 units tall, and then 3.095 units tall, whatever. This part's easy. We can keep on repeating it, just getting more and more and more and more and more rectangles until we have so many rectangles that the area under the area of all of these rectangles is basically the same as the area under the curve. You can see there's not much room left here for improvement. So now that we understand the basic idea, we're going to take the integral. We're going to find all of this area by creating increasingly fine rectangles, increasingly fine meaning increasingly narrow rectangles, until they're so narrow that we get the area under the curve. We can use this approach for any curve. Here I've just configured it, for whatever, f of x equals this mess. Let's say I had cos of x. You see, it's still working. Let's say we can create either very not good approaches, or we could create like more and more and more accurate approaches. And we're doing the same thing every time, every approach. Let's say we had f of x equals e to the x. It's going a little bit off the screen, so I'm just gonna try and get it back onto the screen. There we are. Same thing again, right? Break it up into smaller rectangles, and then when we have very, very small, very, very narrow rectangles, I should say, we can just calculate the area of all of those rectangles, add them up, and there's our integral. This, I suggest to you, is how Desmos figured out the answer here. This is an approach called discretization. Discretization, I don't know, something along, it's discretization, like that. So this approach just means discrete, that means different, right? Discretization, make differentization, that's our process. We're creating different chunks of this integral so that we can add up the area across all of the chunks and get an estimate for what the actual area is. We do have to do this in some cases. We have sometimes simple integrals that we know how to calculate the area of, but then other times we have no clue how to calculate the area under some line, and we do need the help of discretization. For example, let's say I have a very annoying equation, the square root of the square root of the square root of the square root of x. How about ln x? How about e to the square root of x? This is a very not friendly curve. I wonder if my... Nope. Oh, it does work still. There we are, you see? So we're creating more and more rectangles underneath the curve so that we can approximate the area of whatever this mess is. And there is no way that we would have been able to use formulas or wanted to have used formulas to clean up some mess like this. So here's the magic approach in visual form. I will just make one quick comment. Let's just have a simple quadratic here. It goes off the screen. Okay, fine. How about, okay, we have a simple square root of x thingy, or yeah. So this is our equation. Make it a little bigger. There we are. One thing you might have noticed as an issue is that whenever we have these boxes, come on, why are you not cooperating? No. Okay, let's just go back to e to the x. There we are. Whenever we have these boxes, you see, it's always an underestimate. Why is it always an underestimate? Because no matter how many rectangles I create, I set this up to ensure that the left corner of these rectangles, it touches the curve. I could do the same thing, but just be like, okay, make the rectangles as high as you can until the right corner is touching the curve. So if I did that, here's what we would have. Now we're making the rectangles as tall as possible with the right corner still touching the curve. And now you can see I'm overestimating. Same thing if I get more precise. right? I'm still overestimating, right? I can keep on getting more and more precise. I'm still overestimating. So this is the difference between what we call a left integral and a right integral. With the left integral, for each of these rectangles, we're taking the left-hand corner, and then we're going to raise the height of the rectangle until that left-hand corner is touching the curve. For the right-hand integral, what we're doing is for each of these smaller rectangles, raising the rectangle until the right-hand corner is touching the curve. So this is going to lead to under versus overestimates. One thing that you should keep in mind, and you may have noticed this even when I showed you the cos of x function, the only reason right integrals corresponded with an overestimate was because this was an increasing function in the area that we wanted to take an integral over here. When we had cos x, if you see in this area now it's a decreasing function, and now this right integral is an underestimate. So let me make this larger so you can see. So you see this right integral, it's now an underestimate because now we have a decreasing interval in fancy words, and the left integral is an overestimate. So these are just some things to keep in mind as you look into integration. I hope that these visuals show the concept, because I really hate when we get so lost in the formulas and numbers that we don't remember what we're doing. What we're doing is discretization, works with any function. It's our workhorse for how to calculate integrals, areas under the curve.